Hey everyone, welcome. Today we're tackling a Leetcode problem called maximize the number of target nodes after connecting trees wine. It sounds a bit involved with trees and targets, but don't worry, we'll break it down step by step. Alright, so here's the gist. We're given two separate trees. Think of them as two different networks of nodes. We also get an integer, let's call it. The main task is this. For each node in the first tree, we need to figure out the best way to connect that specific node to some node in the second tree. When we make this temporary connection, some nodes become target nodes. A node is a target to another node if the path between them has or fewer edges. And a node is always a target to itself. Our goal is to find, for each starting node in the first tree, the maximum total number of nodes that become target to it, after making that optimal one-edge connection to the second tree. We'll return an array of these maximum counts. And just a heads up, each of these connection scenarios is independent. We undo the connection before considering the next starting node from the first tree. Let's walk through the example. We have two trees. Presententiamindastable is 2. This value means a node is a target if it's at most 2 hops away. The output, 9, 7, 9, 8, 8, means if we consider node 0 from the first tree as our connection point, the max targets it can have is 9. If we consider node 1 from the first tree, the max is 7, and so on. How do we get these numbers? That's what we need to figure out. So when we're trying to find the answer for a specific node in the first tree, let's call it node I from tree 1. Two groups of nodes can become its targets. First, nodes that are already in the first tree and are close enough to node I, meaning within hops. Second, nodes in the second tree. If we connect node I from tree 1 to some node j from tree 2, then nodes in the second tree can also become targets to node I from tree 1. The path to these second tree nodes would go from node I from tree 1, then take that new connecting edge to node j from tree 2, and then continue within the second tree. Let's get specific about distances. For nodes within the first tree, it's straightforward. We count how many nodes are or fewer hops away from our node I from tree 1. We can do this with a search, like a depth-first search or DFS. Now for the second tree. If node I from tree 1 is connected to node j from tree 2, any target node in the second tree, let's call it node q, must be reached by a path like node I from tree 1, then one hop to node j from tree 2, then some hops from node j from tree 2 to node q. If the total path length must be at most, and one hop is used for the connection itself, then the path from node j from tree 2 to node q inside the second tree must be at most k-1 hops. This k-1 inside is key. For any node in the second tree, we can calculate how many nodes, including itself, are within k-1 hops from it. Let's call this count2 of j. Since we want to maximize the targets, when we connect node I from tree 1, we should connect it to the node j from tree 2 that gives the biggest possible count2 of j. So here's the plan. First, we'll go through all nodes in the second tree. For each one, we'll run a DFS to count how many nodes are within k-1 distance. We find the maximum among these counts. Let's call this max contribution from tree 2. This value is fixed, no matter which node from the first tree we're considering. Then, for each node I in the first tree, we run a DFS from node I to count nodes in the first tree within distance. Let's call this count1 of I. The total maximum targets for node I will simply be count1 of I plus that max contribution from tree 2 we found earlier. To do all this counting, we'll use a depth-first search or DFS. Our DFS function will take the current node we're visiting, the node we came from, its parent, so we don't go backwards, the tree's structure, the adjacency list, and crucially, the number of hops remaining in our budget. If hops remaining drops below 0, it means we've gone too far, so we count 0 nodes from that path. Otherwise, we count the current node itself. That's one target found. Then, for each of its neighbors, except the one we just came from, we recursively call DFS. For these calls, the hops remaining will be 1 less, because we've used up 1 hop to get to that neighbor. We sum up all these counts. Alright, here's the Python code that puts it all together. Don't worry if it looks like a lot at first glance. We'll highlight the key parts. This is our DFS helper function we just talked about. See, if k_val, our remaining hops, is less than 0, it returns 0. Otherwise, It counts the current node, that's the current underscore sum, equals 1 part, and then tries to visit all its neighbors, reducing k underscore val by 1 for each step. It sums up the counts from all valid paths. First, we need to represent our trees in a way that's easy to work with. We use adjacency lists. For each tree, we create a dictionary where keys are node labels, and values are lists of their neighbors. We iterate through the given edges 1 for the first tree and edges 2 for the second tree to build these lists. We only do this if the trees actually have nodes, of course. Next, we figure out that max contribution from tree 2. If the second tree actually has nodes, that's what m greater than 0 checks, we loop through every single node in it. For each of these nodes, which we can call j node in tree 2, we use our DFS worker. Remember, for the second tree, the distance budget is, quote, k-1. We store all these counts and then find the biggest one. This becomes our max underscore contribution underscore from underscore tree 2. Finally, we get to the main part for the first tree. If the first tree has no nodes, we just return an empty list. Otherwise, we loop through each I node in tree 1. For each of these, we use our DFS worker again, this time on the first tree's adjacency list, add j1, and with the full distance budget. This gives us count underscore from underscore tree 1. The answer for this I node is then count underscore from underscore tree 1, plus the max underscore contribution underscore from underscore tree 2 we calculated earlier. We add this to our list of results, and once we've done this for all nodes in the first tree, we return the complete list. So how efficient is this approach? For time complexity, we build adjacency lists, which is proportional to the number of nodes and edges, roughly order n plus m, where n is nodes in the first tree and m is for the second. Then, we run a DFS from each of the m nodes in the second tree. Each DFS takes about order m time, so that's m times m, or order m squared. After that, we run a DFS from each of the n nodes in the first tree. Each DFS takes about order n time, so that's n times n, or order n squared. Putting it all together, the total time complexity is roughly order n squared plus m squared. Given that n and m can be up to 100, n squared is 10,000, so this should be perfectly fine. For space complexity, we store the adjacency lists, which take order n plus m space. The recursion depth of our DFS can also go up to n or m in the worst case for a path-like tree, so space is order n plus m. So to wrap this up, the core idea was to split the problem into two parts, counting targets from the first tree and counting potential targets from the second tree. The really important trick was realizing that if we use one hop to connect the trees, the remaining distance budget for paths within the second tree becomes k-1. By pre-calculating the best possible number of targets we could get from the second tree, we could then simply add this fixed amount to the count we get from the first tree for each query node. And, as often is the case with tree problems, depth-first search was a super helpful tool for exploring and counting nodes within a certain number of hops. Hope that breakdown made sense and helped you understand the solution. If it did, feel free to hit that like button, subscribe for more Leetcode explanations, or drop a comment if you have any questions or thoughts. And hey, if you're feeling extra generous, you know where to find the Boba Fund. Keep practicing, keep coding, and I'll catch you in the next one.